right, who remembers this from 2 years ago? Good, we got some faithful in here. That's great. Back then, I talked about the common pattern of the application-centered data center, or ACDC, right? And how it's taking us on a journey to a place that we really don't want to be going, right? I talked about how the typical application development pattern combined with the ETL-ridden warehousing and reporting method results in hundreds and sometimes even thousands of data silos across organizations. I want you to imagine that you have this problem. It shouldn't be too hard, right? Now imagine that each one of these silos contains some important data about some aspect of something that you care about, like a customer, for example. Your view of the customer may look like this. Can you really see your customer? Do you really know him? This is how most of your customers look to you, and this is how you look like to most of the organizations that serve you. That explains a lot, doesn't it? So last year, just a quick show of hands, how many of you switched brands or business due to poor customer service? Oh, not too many. Okay, well, in a recent global survey, that number was 66%. And of those who switched, 82% said that the brand could have done something to stop them. So as omni-channel becomes more omni, and the data that we have about customers comes from more and more different sources, it becomes both more difficult and more important to integrate all that data to really know your customer. In a 2013 study, over 1,000 consumers were tested in lab conditions, and for the majority of them, just thinking about receiving great customer service triggered the same cerebral reactions as feeling loved. Do your customers literally feel loved when they deal with you? Can you give them that experience if your view of the customer looks like this, or would it be better to have a view that looks something more like this? Right? And in case you don't care about customers, right? I mean, really, some of you may have a problem that has nothing to do with customers. I mean, maybe these little puzzle pieces are trades or components in a bill of materials or adverse events reported to a federal agency or evidence in a life sciences efficacy study or potentially fraudulent transactions or anything else that you care about but just can't see because it's too difficult to even find the pieces, much less bring them all together into a coherent picture. Can you assess your risk across a portfolio of trades fast enough to mitigate it? Can you get ahead of a drug recall before it spirals out of control? Can you see the impact of patient treatment fast enough to intervene? And can you see a fraudulent transaction pattern in time to take action? Can you do any of this with a siloed, fragmented view of what's important to you? Think about these questions. They have something in common besides just bringing data from multiple silos together. They're not about pulling data together into a report or a data warehouse for later consumption. They're not about observing what just happened. They're about changing what happens next. They're not observe the business questions. They're run the business questions. So clearly, pulling all of these puzzle pieces together is important. But how do you actually do it? So to illustrate the problem, let's assume that you have multiple systems containing silos of data about customers, products, and the transactions that customers have made. Conceptually, your model looks like this, right? One customer can have many transactions. Each transaction can involve many products, and each product can, of course, be involved in many transactions as well. This thing up here is a very simplified, for those data architects out there, please don't complain later, very simplified version of something called an entity relationship diagram, right? It shows you the things that you care about, entities, and how they're related, the relationships. So there are several ways to model this in a traditional relational system. And chances are, if you have this data in more than one system, the physical models are different in each system. That's part of the problem. It's hard to bring data together when the models are different. So let's take a look at the physical model for one of these systems. A physical model is called a schema, right? In a relational database, the schema consists of a set of interrelated tables. Each table can only contain flat rows. So generally, a single entity, like transactions in this case, is split across multiple related tables. This schema here has a bare minimum of information. It's a very simple schema, but already it's pretty abstract. It takes a little squinting to even understand this model. So, for example, what's this address thing? Is that the full address, or is it just a part of the address? I think it's just the street part of the address. I infer that because there's also a city, state, and zip after that, right? But even this simple model may be too simple. So what if a customer has more than one phone number? I guess in this database they don't, because there's nowhere to put that. Okay, so let's look at the equivalent schema from our second system. Remember, we're integrating data that's conceptually the same, right? Customers, transactions, products from two different systems. So here's our customer table from our second system. That looks a lot simpler, but maybe some stuff's missing, like city, state, and zip. Maybe shipping address and billing address are just free-form text fields. And what about the phone number? Okay, let's dig a little bit deeper. Oh, okay, this isn't actually simpler. It's more complex. It looks like customers can have two addresses, and they're in a different table, and they can also have as many phone numbers as they want. That's more realistic, right? But in a relational database, if you want to model many addresses or many phone numbers, you need a whole different table for that. So let's look at the rest of the schema. Okay, so this system calls transactions orders. A lot of the other stuff is basically similar, but what's this supplier ID? I don't see a suppliers table, so we may have to actually look at some data to figure out what this actually really is. So you get the idea. These are two pretty simple, conceptually similar, but physically different data models. How would we approach bringing this together in a traditional relational system? So first we'd have to ensure that we'd really figured out what all this stuff is. We'd have to know, for example, what is that supplier ID? Not sure what that is, but we'd better figure that out up front. Because then we would need to build a new schema, right? A third physical model that supersets these two models. In this case, that might not be too hard. But in a real-life system with a schema that looks more like this, that can be incredibly difficult. And those of you who've done this before know that even this one is actually pretty simple compared to some of the schemas that you have in your systems. If you had a data integration problem that involved 30 schemas that look like this, you'd start to think about maybe dropping some low-priority data on the floor, right? So that you didn't have to model it 30 times. In a relational world, that's really the only way this problem is going to be tractable at all. So back in our simple world, right, you may say, well, maybe we don't need the transaction status from that first model. And, do we really need shipping address, or can we get away with taking that out? And wow, it would really simplify the model if we could just, assume one phone number for each customer. That would really simplify things. So who's done this kind of thing before? So who has done a data integration problem where you've had to leave data behind because you didn't need it and it was just too expensive to model every possible piece of all the source schemas? Put your hands up. All right, higher. Great, thank you. Leave them up. All right, leave your hands up if you later had a new requirement, like either a functional requirement or a governance requirement, that required some of that data that you left behind. Okay, so I still see a lot of hands. Those of you who put your hands down, put them back up again if you ended up with a master data problem because your new schema looked different from your old schema, and consumers of your data were unclear which was supposed to be the master, right? Okay, last question. Who has actually succeeded in using a relational technology to integrate something that looks like this with something else that looks like this, excuse me, only to later find out that you need to fold in something new that looks something like this, right? How hard is that? It basically involves starting over. So you get the idea. I'm not going to keep going along these lines because I want to show you the right way to do this. But keep in mind, we're only at the schema design stage here. At this point, we haven't even built an integrated database, much less loaded any data into it. So with a relational technology, we can't do that until we figured out what our new schema is going to be. What's more, in a real project, we'd also have to figure out how to actually map all this stuff into the new schema, including how to handle all the exception cases, like garbage data in a typed field. I get to say stuff like garbage data in a typed field because I'm in engineering. But we also have to figure out how to retain metadata about the source of all these data elements, right? And what transformations we did to get it to fit in our new schema. And we also have to code up all the ETL jobs that would physically move the data and transform it along the way. And if we want to capture changes to our data or changes to the model or the schema over time, we'd need to find and figure out a way to version all this stuff. All this before we can load a single record into our new database. I'm exhausted just thinking about this. Better. Okay, so once you're done with all this, assuming that you succeeded, do you end up with a schema that can be generically reused as a canonical model in your organization? No. You end up with an even more complex model that's specific to this particular application, something that contains portions of data from lots of different places, transformed in a way that's not transparent, into a new schema that's optimized for this particular use and is not reusable. Congratulations, you've just created another silo. No matter what you do, no matter how hard you try, you're stuck in this fragmented rows and columns world, this rigid matrix that controls everything you do. You're a slave to the machines, bending your will to conform to their strict rules, shaping your world to the tyranny of their structures. Take the red pill, free your mind. Forget everything you think you know about how to model and integrate data, and I will show you a better way. But before we get too far down the rabbit hole into Wonderland, it's probably worth taking a little time to think about some goals and principles to talk about how we're going to frame this problem. So first, the goal. We're not just building an application. We are building a silo-busting operational data hub. Sure, maybe there's one specific use case that we're going to start out with, but the larger goal is to permanently bust the silos so that the data can be open to many use cases, not just create a new silo that works only with one use case. So ultimately, we are building a canonical entity model. What does that mean? This means that we're building something that represents the data independent of the use case for that data, something that's usable for any use case, not just for a specific one. But we can't afford to drop any data on the floor during integration because we may need it for some future use case. And we need to be able to balance preserving data as is with cleaning it up if it's garbage. So we may need to make some transformations, but we must be able to preserve the lineage of the data, meaning how the data got into the state that it's currently in. Now, we may also be getting data about the same entity from multiple different systems, and some of that data may conflict. Right? So to resolve this, we have to be able to preserve the provenance and the context of the data as well. And of course, we have to be able to govern the data, right, consistently, according to our security, privacy, lifecycle, retention, compliance, and other data-based governance and policy rules. And we should be able to do this independent of the application that's using the data. So in other words, unlike business logic, governance is not a function of the application. Governance rules are properties of the data itself. So your data hub should manage them on behalf of the applications that use it. Now, as we pursue the goal, we need to be realistic. We work within an organization that has to get stuff done and can't wait for us to re-engineer the whole data landscape. We don't have the luxury of forcing everyone else to adapt their legacy silos to our shiny new system. We have to be able to take what they can provide. Also, we need to provide business value quickly. We can't wait until everyone is on the system before anyone gets any benefit. Plus, data changes. Business rules change. Policies change. Use cases for data change. We need to be able to adapt to change. So we need to take an evolutionary approach. We can't collect all the requirements across the whole organization in advance and then build something that's set in concrete. It'll have to be able to adapt and change probably forever. So the bottom line is we need to be able to take idiomatic representations of data in with all their quirkiness and provide clean canonical representations out. And provenance and lineage must be preserved and governance enforced in the hub itself. And we need an evolutionary approach that can continue to evolve and adapt over time. Okay, so let's get started. Let's start with our first model. Remember, we're still in the matrix here, right? So let's look at what an entity, an actual customer, looks like in this model. It's a row in the customer's table. Well, wait a minute, what's that in the phone column? I guess we were wrong earlier. There are sometimes two phone numbers in there. It's just that rather than change the schema, right, like Jeff said, whoo, don't touch the schema, the developers just cheated on the schema. They cheated on the schema by cramming two phone numbers in the same column. Now, I'm not going to ask any of you if you've done this before. But I will ask if you know of someone who's done this before. Yeah, okay, some hands coming up now, right? Yeah, it's actually pretty common because once a schema exists in a relational database, it's hard to change, right? It's much easier just to code around the problem. And in today's world, when you have to get results quickly, that's the only way to get things done. But it does cause problems because now anybody looking at the schema documentation is going to be misled. You have to actually look through the code to find these special cases. So right away, we have some data quality problems, but no worries, we can deal with that. Let's take a look at our second schema. Right? So a customer in this schema is actually broken up across 3 or more rows in 3 different tables. Let's take a look. So it looks like Karen has 2 phone numbers, but in this case, we don't need to cheat on our schema because the schema can accommodate more than one. But Karen's simple record here, simple record, is split into 5 rows across 3 different tables. Now remember, this is a very simple example. It can get way more complicated than this in real life. So, as you all know, relational databases reassemble this customer by joining these rows along these primary foreign key relationships. In your application, you use a 4-letter word called ORM for this. Trust me, it's 4 letters. Right? So, here's what 2 customers from our 2 different systems look like in your relational world. That's pretty different. And this is the crux of the problem. In the relational paradigm, we're stuck trying to force-fit these 2 very different shaped customer records with their own semantics and idiosyncratic representations into the same database. But if we think outside the rigid rows and columns of the matrix, we can see that there's another much more natural way to represent these customers. So here I've represented them as documents, like you might see them in a form or in a message passed between systems in your organization. You can tell it's a much more natural way to represent them because it's just much easier to read. All the attributes of the customer right there in front of us. We don't need to go hunting around in different tables to find them. You can represent multiple repeating attributes like phone numbers or hierarchical attributes like addresses easily without having to build out separate tables. But most importantly, unlike relational representation here, where the 2 customer records are different shapes and therefore can't be mixed into the same database, these 2 documents can easily be put in the same MarkLogic database without any modification at all. They can live harmoniously, side by side, and they can be searched and queried together. So for example, if I do a search for the zip code 94111, I'll find both of these records. So how do you convert these types of tables into documents like this one? Well, chances are you're already doing it, because this document representation is what you put on a message bus when you send objects from one database to another. And it's also what you send to your application when you want to show this data in a user interface. And if you're not already doing it, then you can ask your relational system to produce this for you, because any relational database can produce a denormalized view of an entity like this pretty easily. All right, so let's review the story so far. So far, we've only covered getting data into our integrated hub. With a relational technology, here's how you do it. Step 1, gather all the schemas that you want to integrate because you'll need to superset them all. Step 2, squint at the schemas. Figure out what they mean, how they work, what they have in common. You may need to look at your data, and in some cases, your actual code to really make sense of them. If you have documentation, that's great, but know that it's likely unreliable because at some point, some developer probably cheated on the schema, right? Step 3, decide what you're willing to drop on the floor, because if you try to rationalize all the schemas from all your silos, you'll never get it done. Step 4, build a new schema that can accommodate all the data you decide to keep from all these different systems. Step 5, write ETL jobs to extract the data from the source, transform it into your new schema, and then load it into a new database with the target schema. All right, here's how you do that with MarkLogic. Step 1, pick a couple of sources to start with. You can always add more, right? And dump some sample records out of them. Step 2, load those into MarkLogic as is, and then use MarkLogic's powerful built-in search capability to help you understand what you have. Much easier. Now, if you're following closely, you'll notice that although I said you can search for 94111 and find both these records in MarkLogic, the data isn't really unified. There isn't a single concept of zip code that works across both of these objects. right? In a relational project, you would have had to harmonize that before you loaded it. It was either that or just not bring the zip code along. So in fact, you would have spent a lot of time harmonizing all the attributes for all the entities across all the source schemas, whether you needed them or not. It was that or leave them behind. Do you need to query zip code? Maybe you do, maybe you don't. Why should you do work to rationalize and harmonize data models if you're not going to use that work? Wouldn't you rather be able to do that if and only if you need it? With MarkLogic, you can, so let's take a look at how that works. Of course, you can start by just querying for zip and postal right together. So it's easy to do in MarkLogic, and now you're querying consistently. In fact, while you explore the data and figure out what might be valuable and what might not, this is a really good way to do these kinds of queries without doing any transformation or modification to your data at all. But once you understand what you have, right, and you know that you'll want to query consistently across these different sources, you'll want to harmonize that in the database. So a best practice data integration pattern in MarkLogic, which you'll hear about probably ad nauseum this week, is called the envelope pattern. So this basically means bringing your data into MarkLogic as is, like we've already done here, and then building an envelope, adding an envelope around it that contains only the canonical data elements that you actually need. If later on you need more, you can always add more, so don't try to boil the ocean here. So here are two documents with an envelope, empty envelope added. I've called it canonical because that's where my canonical model is going to go. All right, so now let's look at how we might fill these envelopes for our two different customers. In our example, just imagine that the first use case for this harmonized data is an application that can show us how many customers we have in each geography and what products they bought, and maybe allow you to drill down by product category, product type, or maybe full text product descriptions. In our case, our geographies are defined by zip codes, so we'll want to query consistently across zip code. So how do we do that? Well, now that we've decided that we want to query customers by zip code, we simply just promote the zip code from the source into the envelope, like this. Right? You can put anything you want in the envelope, and once it's there, you can query it consistently across all your data sources. So let me repeat that. Everything that you put in the record is automatically queryable. Just by adding it to your data, that adds it to the schema. That's the power of MarkLogic's universal index. What you're effectively doing here is building up your canonical data model in an agile way from the ground up. Your model can meet the combined requirements of all the applications and services that need to consume your data, but each application only needs to understand the parts of the model that it actually uses. And because there's a consistent canonical form in each record, consumers of the data from your data hub will know how to use it without having to know how to read the schemas of all the original source upstream systems. So this is different from ETL in several key ways, all of which make it both faster and more flexible. First, you only need to harmonize the things that you or your consumers want to query or use consistently across the sources. No need to create one schema to rule them all. Just promote what you need into the envelope and you're off. This has the added benefit that you're explicitly not transforming the source content. You get to preserve and even query all of the source content as it came out of your source system without modification. This is really handy for when you suddenly get a new requirement that requires some of that data. If you ever need to change the model, you don't have to go back to the source system, right? The data is right there in your database. This also makes it easy to preserve the data lineage. Remember the governance principles. Lineage and provenance must be preserved. You can stick those in the envelope as well. Or you can create another envelope for metadata, like this one. Remember that everything that you put in the record is automatically queryable. So now you can do queries based on provenance or lineage of data as well as the data content itself. So let's say you find a bug in your transform that could cause a data quality problem. It's trivial to find all of the records that are impacted, and you can actually fix them because you still have the source right there. But that's not all. For each new source you want to integrate in the future, you only have to figure out how to transform the data in that source to your canonical envelope form. If your source schema doesn't have something that's in your canonical form, like maybe it doesn't have a zip code, then you just don't put anything there. If it has something new that you want in your canonical model, you just add it. You don't need to go rebuild your whole database because a change to the canonical model from integrating a new schema doesn't require any change. It doesn't impact any of your existing data or require any change to any of the services consuming your data. So, for example, Let's imagine that you have this little record from a database of Twitter handles that you're storing somewhere. Right? This little record can live quite happily alongside these other records in MarkLogic. You can enhance it with metadata and put it in the envelope like that. But there's no zip code in here, right? But you do want the Twitter handle to be in your canonical model, right? So that's what you put there. Now, look at these three envelopes. When you decided to add the Twitter handle to the canonical model, you didn't have to go back and change your existing records because they didn't have a Twitter handle. Similarly, this record doesn't have a zip, so you just leave it out. These three envelopes are different, but they're not inconsistent. You could query them consistently. Effectively, you could have multiple versions of the canonical model in the database at the same time. Most of the changes to the model will be additive, like this one. So existing consumers of the data don't need to make any change. Even for changes that aren't purely additive, it's easy to make them in a backward compatible way, so that changes to downstream applications to leverage that new data doesn't need to be synchronized with changes to the data hub itself. So the overall result is a much quicker, more agile method of data integration that can produce business value immediately without risk to existing applications, and then extend that value indefinitely as new data sources or uses for existing data are uncovered. Wow, that's powerful stuff, right? Yes, it is. Thank you. Okay. I had to beg for that one. You can see that with MarkLogic's universal index, the document model, where anything can be added to any record and is immediately queryable in a structured way, is way more powerful and flexible than the related table model of a relational database for storing rich representations of business-level entities like customers, transactions, and products. But what about the relationships between those entities? Right? We want to be able to store and manage and query those as well, right? I mean, it's all well and good to know who our customers are, but don't we also want to know what products they bought? Of course we do. So let's see how that works. Remember this model? So let's look at all the data for a single transaction, which this model calls an order. Wow, look at all those joins. To render this data into a view that you actually care about requires knowledge of how these tables are actually structured, so you can tell the database what to select and from which table. If you want to do the same query across 30 different physical models, I'm afraid that's 30 different queries, each requiring some understanding of the table structure of the physical models. Each of these queries also requires a bunch of joins. Relational technologies are pretty good at doing joins, but they're still expensive. So remember, this is a really simple model, right? Most models have hundreds or thousands of tables. This one only has 6. Okay, so remember, a relational database reconstitutes records and assembles data by joining along these primary foreign key relationships. So if a line item references order 8001 and product 7001, and order 8001 is for customer 2001 who has a shipping address 3001, then maybe I shipped a really nice laptop to Karen in San Francisco on the 4th of April, right? But maybe not, because these tables actually tell us nothing about the actual nature of the relationship, only that one exists. The column title can sometimes give us a hint, but the actual nature of this relationship is buried in the application code. If you want to be sure of what the relationship means, then you have to look at the code. Now, some of these joins represent real relationships that we would understand in the business context, and some of them are spurious relationships that exist only because the relational model isn't rich enough to accommodate anything other than a row in a table. How can we tell which is which? Well, without some knowledge of the semantics of the model, we really can't. So there we go. Maybe that'll help. I've removed the spurious relationships and kept only the ones that are actually reflective of business concepts, customers, project, transactions, and products, right? It's tempting to say that this tells us that this customer bought these 2 products, but in reality, all it tells us is that this customer has some relationship with an order that's related in some way to these 2 products. Because remember, the nature of the relationship is not in the database, it's in the code. So let's take a look at the document representation for this transaction. So first of all, this is way more natural and easy to read. And second, these documents map directly to our conceptual model that we have for our business. Customers, transactions, products, right? Remember the entity relationship diagram from way back? Right? Here it is, reflected directly in our database. The entities are denormalized. There's no need to hunt around lots of different tables and do a bunch of joins just to see what an order looks like. Only the relationships that actually matter remain. So let's talk about how to model them. So if we do nothing at all, we can still query these relationships. Why? Because the primary foreign key mappings are still there in our data. Remember, we loaded it as is. But these mappings still suffer from the same problems they had in the relational world. In particular, the nature of the relationship is nowhere in the database. To solve that problem, we use semantics technology. Semantics is a way to express very granular facts using what's called a triple. A triple is called a triple because it consists of three things: a subject, a predicate, and an object. In other words, two things and the relationship between them. So here's an example with three triples. Customer 2001 placed order 8001. Order 8001 contains product 7001. Order 8001 contains product 7002. Three simple facts that describe relationships. When we combine these three facts, we get a graph like this one. We can use a language called Sparkle to query this graph. So for example, this simple query here means show me all the customers who placed an order that contains product 7002. But unlike primary foreign key mappings in a relational database, these facts have meaning because we can define what it means to place an order and what it means for an order to contain something. For example, we could build a rule that says if a customer placed an order and that order contains a product, then the customer bought that product. Right? If we do, then we've just invented new facts about our data based on the semantic meaning that was inherent in the facts that we already had. Now we can simply query to find all customers who bought a product, right, bypassing the organizational structure of the data entirely and getting right to its conceptual meaning. So you can imagine how far we could take this. Right? Triples don't just have to relate entities to other entities. They can relate entities to concepts, and they can relate concepts to other concepts. So for example, if the power supply is part of a set of products like accessories, and accessories complement other products, you could model this in your database. Why? Because if someone buys a laptop, you may want to suggest accessories that go with that laptop. Or if someone buys a laptop and has it shipped to someone else, and that person also has an e-commerce account with us, you may want to suggest accessories for that laptop next time that person signs in. So you may think we're digressing from this whole data integration thing, right? But consider the fact that someone shipped a laptop to someone else, maybe in one system, the fact that that person has an e-commerce account with us, maybe in another system. It's only when you bring these facts together with their meaning intact that the magic happens. So you can even store your data dictionary in the database along with the data. So the meaning of the relationships themselves can be preserved in both human and machine readable form. Relationships in a relational database are weak. They mean nothing. Any meaning you give them is obfuscated in application code, and any piece of code that queries that data had better have the same understanding of its meaning. Semantic relationships in MarkLogic are rich with meaning. You can define that meaning explicitly. You can query that meaning directly. You can draw new inferences from that meaning and create new information. So how do we encode this meaning in our data? Simple. Here I've added a new triples wrapper to our data in addition to the metadata and the envelope that I talked about earlier. So this defines all the relationships between our entities. MarkLogic will automatically index these as triples, which can be joined, queried, combined with other triples, and used to build inferences. And triples can go anywhere in your document, but because I like things clean and orderly, I decided to put them all together. That's it. That's all you have to do to leverage the power of semantics. So the overall pattern here should be clear by now. You can take data from multiple different sources as is in its natural form, enrich it over time to harmonize it or to preserve metadata and context, or to drive synergy with other data through the power of semantics. And as you enrich the data, your schema automatically evolves because MarkLogic sees the new data you've added and makes it queryable for you. So let's recap. Relational databases are bad at representing entities because they flatten every piece of a complex entity out into a bunch of tables that are only related because they have to fit the model. And all these tables need to be rejoined at query time in order to reconstitute the entity. Also, you have to decide in advance how to model all the attributes of all the entities that you care about. Relational databases are also bad at representing relationships because it's hard to distinguish the real relationships from the spurious ones that exist only to allow reconstruction of the entities that they had to smash apart in the first place. And anyway, those relationships have no meaning in the database. You have to look at the code to figure out what they actually mean. MarkLogic is great at representing both of these things in a much more natural way because documents are best for entities and triples are best for relationships. And MarkLogic supports both natively and allows you to query them together. In addition, MarkLogic lets you store original, unadulterated data and a canonical clean form of that data, along with lineage, provenance, and other metadata in the same record, and query all that together. This makes it really easy to store conceptually similar but physically different data from multiple sources in the same database and query it consistently. What's more, you can evolve that canonical representation over time as you need it. You don't have to boil the ocean, which means your project will proceed faster and with less risk and will in fact succeed where many fail. And to top it all off, once the project is done, you've created a new asset for your organization that can continue to evolve and meet your business needs rather than yet another data silo. So MarkLogic makes it easy to bring all this data together to answer those run the business questions. But if you're bringing data and managing data from multiple different silos together in one place, you'd better know that it's secure, that it's available, and then you're able to meet all the rules, regulations, and policies that are required for that data. In other words, you have to be able to govern the data appropriately. Remember I said that governance is a property of the data, not the application that uses that data. In your data hub, many applications will use the same data. It's much easier on them if you can apply these governance rules in the hub itself and not require each of the applications and all of those application developers to understand and apply the same rules consistently in all those applications. Governing the data in your hub gives you a central place to manage and maintain these really important data rules and not worry that they're being followed consistently everywhere in your organization. So we've already talked about some important governance principles: provenance, lineage, and data quality, and how MarkLogic can help you with them. But there are other aspects of governance that are at least as important: security, privacy, compliance, and lifecycle management. MarkLogic has industry-leading capabilities in all these areas to help ensure that your data governance rules are enforced. Granular role or compartment-based access controls ensure that the data is only available to people who are authorized to see it and need to see it. MarkLogic's bitemporal capability automatically tracks all of your data over time, so you always have an understanding of what your data look like at any given point. And MarkLogic's tiered storage capability makes it easy to manage the data as it moves through its life cycle, from hot to warm to offline archive. And of course, your system has to be reliable and available. So whether it's on premises or in the cloud, MarkLogic has proven high availability and replication capabilities that'll keep your data flowing in the most demanding environments, including geographically dispersed environments with limited connectivity. So who's actually doing this today? With relational technology, projects of this type can take years, as Gary said. Since I started speaking about the data-centric model just 2 years ago, hundreds of you have designed, built, and put into production a data-centered integration hub built on MarkLogic. Last year, I told the stories of John, the trade compliance officer, his friend Sarah, the derivatives trader, Karen, the lawyer, Karen's brother, Sergeant Bender, and his colleague, military intelligence Lieutenant Jackson. I told you stories about how data impacts every aspect of their daily lives. But these aren't just their stories. They're stories of real MarkLogic customers who've successfully integrated data silos to create operational, data-driven systems. Today, I want to share one more story. It's a story about why being able to bring data together and see a complete picture is something that I actually care so passionately about. Everywhere in the world, there are children at risk of abuse, neglect, and exploitation. There are multiple agencies who share a mandate to protect these children: police, probation agencies, social services agencies, children's services, and schools. These agencies are staffed with caring, hardworking, well-meaning, and passionate individuals. But each agency only has a slice of the data, a small, sometimes fuzzy piece of a larger picture. They need to share information quickly and efficiently in order to get a clear picture of the environment of a potentially at-risk child, to make a determination as to whether and what intervention is required. To solve this problem, the UK Home Office initiated a program of multi-agency safeguarding hubs to foster the cross-agency collaboration and teamwork that's required to do this important work. This hub is housed in a secure facility where more than 100 people from all the different agencies work together as a single team. But even though they work in the same location, this team had challenges sharing information. Across the 7 agencies, there are more than 50 systems that people would have to log into to search for information to support decision-making on a case. And it's hard to understand the implications of one data point in one system without ready access to all the related data. Something by itself could look unimportant, but taken with other data, it could reveal a pattern that tells a potentially tragic story. Today, MarkLogic are building a system to help these agencies bring this data together so that they can get a clear picture, see the patterns, and reduce the risk of late intervention. That's the power of bringing disparate data together. It can literally save the lives of our most vulnerable children, because children should only have to hide when they're playing hide and seek. Every year, MarkLogic honors customers who've innovated in their industries with our MarkLogic Excellence Awards. MarkLogic Excellence Award goes to the UK Department for Communities and Local Government. Their mission is to create great places to live and work, and to give more power to local people to shape what happens in their area. They have a mandate to support strong communities with excellent services and boost local growth. The DCLG standardized on MarkLogic as their strategic data platform. So they benefit from a common data platform that allows them to deal with multiple different formats easily and reduce the number of costly legacy silos that they have to maintain. Applications built on MarkLogic help the department to serve local government and thereby communities across the UK. And data collected and processed and analyzed in this platform allows DCLG to best direct government funds to where they're needed the most, supporting projects as diverse as building social housing, supporting troubled families, and retraining the homeless to give them a chance to become productive members of society. So please help me congratulate, also not here today, but we'll be in London, the DCLG. Our next MarkLogic Excellence Award goes to a company that has built not one, but 2 major data hubs in the last 2 years. Aetna started their MarkLogic journey by building a data hub for all their HR-related activity. The HR hub joins over 300 disparate sources of data into MarkLogic and provides over 200 outputs, all while tracking the complex history of the data. The rapid success of that project prompted Aetna to expand their efforts and build the Vision 2020 Enterprise Data Hub to provide interoperability between all of Aetna's platforms and components. So this hub actually exemplifies the best practice patterns I talked about today, creating a plug-and-play architecture that provides the agility to accommodate changes in business strategy and software products quickly and easily. And if you want to learn more about it, you can attend their breakout session immediately following this break. So accepting the award for the Aetna team is Mike Fillion.
David,
Mike here?
Mike had to step out for a meeting with his CIO, something about buying more MarkLogic, I think. But if Igor Board is in the audience, also
Mike, when you're ready, your award's right here.
Is Igor Board can accept it. Mike would like Igor to accept it on his behalf. So Igor Board from Aetna.
Miss Worldwide, let's celebrate. Yeah, yeah. I just wanna celebrate.
There you go.
I just wanna celebrate.
Thank you. Finally, we have the Christopher Lindblad Award. Named for MarkLogic's founder and chief architect, this award recognizes a specific individual who's gone above and beyond to successfully innovate within their organization. Anthony Accardo is director of R&D for Disney ABC Television Group. His Disney career began in 2010 at Disney Research, and in 2012 he moved to Disney's Applied R&D division, reporting to the CTO, with responsibility for evaluating new technologies. Under his leadership, Disney developed a groundbreaking, queryable, dynamic semantic metadata hub. The success of that hub led Anthony to promote innovation and change beyond ABC TV to Disney Studios and Disney Parks and Resorts. But Anthony's leadership also extends beyond Disney. He's been consistently generous in sharing what he's learned with others on this journey through presentations on his innovative use of semantics at venues like MarkLogic World 2015 in San Francisco and in Tokyo, Japan. Most recently, Anthony and the Disney team were key contributors to a project at the University of Southern California's Entertainment Technology Center, using MarkLogic to capture metadata as part of the pre-production process in creating a short film called The Suitcase. And USC is actually here. They're going to be presenting the results of that work in a breakout session tomorrow morning. So please join me in congratulating this year's Lindblad Award winner, Anthony Accardo. Anthony, are you here?
Miss Worldwide, let's celebrate. Yeah, yeah. I just wanna celebrate.
Congratulations, man.
Just wanna celebrate. Tonight we making history. I just wanna celebrate. We've been around the world, say so.
Tomorrow morning, Joe Pascal will talk about some of the incredible things that we're doing to take all this capability to the next level. But as you hear about where we're going, keep in mind what Gary said earlier, that every significant capability that we add to MarkLogic is inspired by the amazing things that our customers and our partners do with the product. So if you're a customer or if you're a partner, thank you. If you're new to MarkLogic, this week will afford you the opportunity to talk to some true visionaries who have escaped the matrix and built some driven innovation and transformational change within their industry. Some of the things that they've done with this advanced technology may seem like magic, but as you listen and learn from them, think about the data challenges in your organization and choose. Choose to stay in the comfortable but futile environment of the matrix, or choose to take the red pill, free your mind, and find a better way. It's not magic, it's MarkLogic. Thank you.